Hello, welcome to this online session on Optimum design. You must have solved so far number of problems in machine design. If I think of a simple design problem, for example this way, a bar is subjected to tensile force of 4000 Newton, design the bar. Assume factor of safety as 2. Material to be selected is plain carbon steel with SYT is equal to 400 Newton per mm square. If you want to solve this simple numerical, what you will think? You will think this way, that since the bar is subjected to tensile force, the induced stress is tensile in nature. That's why sigma T is equal to force divided by cross-sectional area. And this induced stress, that is induced tensile stress sigma T, will equate to permissible stress. Permissible stress is given by SYT by factor of safety. So in turn, your equation becomes SYT by factor of safety is equal to force divided by cross-sectional area or force divided by pi by 4 d square, and hence you will find the diameter d. This is a simple solution of design problem. Solution of a simple design problem. If you want to differentiate a design problem with the design optimization problem, how I can reframe this same problem? I'll reframe this. A tensile bar is subject to tensile force of 4000 Newton. Considering the factor of safety as 2 and length of bar as 400 mm, design the bar with the objective of minimizing the material cost. So something addition I have made here. Addition is this one, that is with the objective of minimizing the material cost. This objective can be different. You can have in the same problem objective as objective of minimizing the material weight. So what you have to understand, that design is still there, but with a addition of some other objective you have to fulfill, right? Of course, the you have to minimize the material cost. It means there must be some available materials, and from which you have to pick the material so that it will give the least material cost. It means we have to find diameter in this problem d in such a way that material cost becomes minimum. So of course, as I said, we must be given a list of material along with cost of material per kg and other required material properties to solve such simple numerical. Material list along with property can be solved clearly. In this problem, to solve this problem, the required parameters are density, material cost, and yield strength. So this is given in tabular form, and we have to select a proper material out of these three, so that we will get the minimum cost. Okay. Now how to solve such numericals? There are different methods of optimization. In this course, we have to study the Johnson's method of optimization. The Johnson method of optimization will go through these three equations: primary design equation, subsidiary design equation, and limit equation. What are these equations? Why they are required to write while solving this, etc. We will come to know when we solve the problem in the next slide. So this is the same problem which I have been written to for the purpose of solution. Again repeat, what is the problem? Simple problem. Simple tensile bar of length 400 mm is subjected to tensile force of 4000 Newton. Factor of safety is 2. Design the bar with the objective of minimizing the material cost out of following materials: tin, carbon steel, aluminum alloy, titanium alloy are given. The densities, material cost, and yield strength are also given in 3 columns. The very first step in the solution, in fact in the solution of every problem in this unit, is to write the primary design equation. Now what is primary design equation? Primary design equation is that equation which gives the value of that parameter which is to be minimized or minimized. For example, In this numerical, you have to minimize the cost. That's why I have written here as a hint to in bracket to write this, think of what is to be minimized or maximized. Since it is to be maximized here, the cost is to be maximized. Anything which you want or anything which you want to be minimized, anything which you want to be minimized is always said to be an undesirable effect. So this undesirable effect, this parameter, that is a cost, is given by cost of material in rupees per kg into kg, that is mass of the bar. So in notations it may be C into M is equal to Cm. Okay. Mass you can replace by volume into density. Density is given. Volume you can replace by area into cross-section area into length. So you get Cm is equal to C into rho into A into L. This A can be replaced as pi by 4 d square also. Okay. Now, what is important to understand here? Cm is to be found out, that's why I made a cross here. C is known, that's why I made a tick. P is, rho is known, that density is known. Area of cross section is not known. L is known. Your purpose is to find out the material cost. For that, entire thing on the right hand side must be known to us. Okay. So all your effort further will be focused on replacing this unknown parameter in terms of known parameter, right? Those will be further steps. But this is a primary design equation. Note I have written, anyhow we have to replace this unknown A, right, by known parameters. So this is my primary design equation. This is my step 1 in all numerics. Step 2 will be to write the subsidiary design equation. Again, for to you take it as a hint to write this, think of type of stress that is induced in the component and corresponding equation. In this equation, in this numerical, the stress is tensile stress. That's why tensile stress is equal to force upon cross sectional area. That's why area is equal to force upon sigma t. So you can replace this A from the in the previous equation. So previous equation was Cm is equal to C into rho into A. A I replace it by F upon sigma t into L as it is. Again, F is known, sigma t is unknown. So next task will be to replace the sigma t again in terms of some known parameter. First step is to write the sigma t in terms of known parameter syt by factor of safety. This is called as a limit equation. So third step is to write the limit equation. Now why this is called a limit equation? Because actual equation is sigma t is less than or equal to syt by factor of safety. Because sigma t, that is induced stress, should be less than or equal to, at the most equal to syt by factor of safety. So it means there is a limit. Sigma t can be as minimum as possible to maximum equal to syt by factor of safety. That's why this is a limit. That's why this is called as a limit equation. Okay. So what we do now further, this sigma t from the previous equation we replace it by syt by factor of safety, and note here that syt is also known, factor of safety is also known. Therefore your Cm becomes, your earlier Cm was C into rho into A into L. You replace A initially by F upon sigma t, and now sigma t is also replaced by syt by factor of safety. So now you note here all parameters on the right hand side are known parameters now. C, material cost given for all materials, density rho given for all materials, F is constant given, syt is given for all materials, factor of safety NF is given, L is given. Okay. So now if we put these values for all materials, we can find out the Cm. To facilitate our solution, what we do, we'll group these parameters. We'll make two groups of these parameters. One group which is dependent on material, and other group which is constant, say, for this numerical. Okay. So C is dependent on material, rho is dependent on material, F is constant for this numerical, SYT is dependent on material, factor of safety is given, okay. L is also constant. Factor of safety is also constant. So we'll group into two parts. One part CM is equal to one part which is, say, not dependent on material into some parameter which are dependent on material. Okay. So that is called as a separation of constant terms and variable terms. So I separated this. Okay. So here you have to take precaution. Okay. That all parameters which are not dependent on the materials you take in one bracket, into all other remaining parameters which are dependent on the material will be in the other bracket. Why it is so? Why what is the purpose of this? By separating these into two brackets, say, this is a constant for all materials. F into NF divided by L is constant for all materials. That's why if we can only find out this parameter, second bracketed parameter for all materials, and the material which will give the least value for this bracketed second bracketed parameter will be obviously the material which will be the least cost, because finally CM should be least. I hope you understand this. Therefore, to find out this parameter for all materials, we take the help of earlier tables. Earlier tables, earlier table in which rho is given, C is given, yield strength is given. We find out the another parameter now, C into rho divided by SY. Only thing that you have to take precaution of unit consistency here. C is in rupees per kg, rho is in kg per meter cube. That's why SYT must be in Newton per meter square, not in Newton per mm square, because in the original table it was given in Newton per mm square. That's why while writing this I have converted into Newton per mm square. Okay, so that precaution you have to take regarding unit consistency. So accordingly, the first number, if you see here, 0.273 into 10 to the power minus 3 is obtained by this way. C, that is 40 into 7800 divided by 400 into 10 to the power 6 is equal to this number 0.273 into 10 to the power minus 3. Similarly, the second number which you see here, 1.253 into 10 to the power minus 3 is obtained by 66 into 2800 divided by 150 into 10 to the power minus 6, 10 to the power 6. This way you get the second number. So you can find the same this parameter C into rho divided by SYT parameter for all the materials which are required. Here three materials are given, that's why we found out the same parameter for three materials. Now obviously the least value is this one, 0.273 among these three, and therefore if it is multiplied by the constant number, it will be again least, is it? Therefore, plain carbon steel, if you choose, will give you the least material, least cost. Right? So one problem is solved here. That which material is to be selected? Plain carbon steel is to be selected. Okay. That's why at this moment these remaining two rows are not of use for us from this point onward, because we will use now these first row only, because that is the only material which will give the least cost. Right? So that is the one part. And now you have to find the diameter. So to find diameter, your equation is the sigma t is equal to SYT by factor of safety, and SYT by factor of safety is equal to force by A. So SYT of which material you will choose now? SYT of plain carbon steel, that is given as 400 Newton per mm square. Here I am putting in Newton per mm square because A I want in mm. So it becomes 400 Newton per meter square divided by factor of safety 2 is equal to 4000 Newton divided by A. So A becomes unknown, you can find out the value of A, and therefore you can find out the value of D. Okay, right? So this is your solution. Along with another answer which you want to quote, which you want to give. What is that cost? You said that minimum cost you will get, but how much cost? The cost you can get by this way. Your earlier primary design equation was this one. C is known, rho is known, A is now known for the chosen material into L. You can find out the value of. You can put the all the numbers here, all the values. Of course, units must be seen here properly. So you get the CM is equal to 0.8736. Almost all problem will go through the same logic. Okay. So I hope you understand the method. If you like it, then I can post few more videos solving few more problems of optimum design. Okay. So thank you very much.